Okie dokie. Last lesson we learned how to factor. Today we're going to learn how to factor something called a perfect square trinomial. So we know how to factor trinomials. You can continue to factor these trinomials today that we're going to learn about using the sum and product chart, but there's actually an easier way. First things first, what does it mean to be a perfect square? A perfect square is any number that you can take the square root of and get an integer. For example, if you had 9's a perfect square, so is 16. So is x squared, right? Because if you take the square root of x squared, you get x. Numbers that are not perfect squares are numbers such as 8 or x cubed or 6. You're looking for any number where you're going to get an integer or a variable answer. And to be a perfect square trinomial, a couple things have to take place. One is that the first and the last terms of the trinomial have to be perfect squares. And the hard part is, if you take the square root of those perfect squares and multiply them together, and then double that number, it has to equal the middle term. And let me try and illustrate that. So if I had x squared plus 6x plus 9. Yeah, I know I just used a lot of fancy words and everything, but the square root of x squared is x. The square root of 9 is 3. If I multiply those two things together, I get 3x. And if I double them, I get 6x. Well, that happens to be, right there, that is a perfect square trinomial. Take this guy. Square root of x squared is x. Square root of 36 is 6. That's 6x times 2 is 12x. Don't worry about whether this is positive or negative. That's a perfect square trinomial. And the interesting thing about perfect square trinomials is that they factor into a single binomial squared. So let's go back to the x squared plus 6x plus 9. Once you realize that that's a perfect square trinomial, so you can kind of say in your head, alright, square root of x squared is x, square root of 9 is 3, 3x times 2 is 6x. Okay, that checks. That's a perfect square trinomial. The factorization is really easy. A single binomial squared, square root of the first term, sine, okay, the polarity of the middle term, square root of the last term. And that's how you factor it. It's as simple as that. And again, if you wanted to check that, that's x plus 3 squared is x plus 3 times x plus 3. You can simply FOIL it out to check and make sure you did it correctly. So the last one we did was x squared minus 12x plus 36. So let's try that. Square root of the first term, sine of the middle term, square root of the last term, squared. And they all work like that. So another perfect square trinomial. Okay, x square root of 25 is 5, 5x times 2, 10x, okay. Square root of the first term, sine of the second term, square root of the third term, squared. Even if the numbers are sometimes bigger. For example, what if you had 16x squared plus 56xy plus 49y squared? Well, ask yourself, is 16x squared a perfect square? I believe it is, as is 49y squared. If I take the square root of both terms, I get 4x and 7y. Multiplied together makes 28xy times 2 is, in fact, 56xy. It is a perfect square trinomial, so square root of the first term, sine of the middle term, square root of the last term, squared. And I've got a few other examples, and then we're going to turn to the idea of what if there's a GCF involved. So this one is ordered backwards. No big deal. We could change the order if we want to, but no need. Square root of the first term, sine of the second term, square root of the last term, squared. The question is, what if you see this? And it's a reminder that whenever you factor, always the first thing that you're looking for is, does what I'm factoring already have a GCF in it? Like for an example, does this have a GCF? I don't think so. If that was a 63 maybe, but it's not. So this is can't be factored. To show you an example of one that has a GCF, Okay, what's the GCF of 16, 36, and 48? Let's go old school. I say old school, we did this a few lessons ago. 16 is 2 to the 4th. 36 is 6 times 6, or 2 squared, 3 squared. Is that right? No? Yeah. And then 48 would be 2 to the 4th times 3. So what do they have in common? It looks like 2 squared, so 4 is the GCF between 16, 36, and 48. And it looks like p squared, so we're going to take a 4p squared out, leaving us 9p squared minus 12p plus 4. But notice, look, square root of the first term, square root of the last term, multiplied together and doubled. After we factored out a GCF, we have a perfect square trinomial, 3p minus 2 squared. And we have to leave that GCF along with our answer. A little tricky. Take some practice.